For those who don't know me, my name's Heather Wood, and I'm the IEST Meetings and Education Program Coordinator. So IEST is a membership association. If you aren't a member, we give technical guidance to professionals working in controlled environments. We help develop, write, and publish industry recommended practices through our working groups, as well as hold conferences and then training classes. So we're going to go ahead and take it away. We'd like for everyone to introduce themselves, including the panelists today. So I'm just going to go down the list that I have here. Please go ahead and just unmute yourself. Let us know your name, company, maybe how long you've been in the industry, and what you're dealing with HALT, HASS, or ESS. So first on my list, I have David. David, you can go ahead.
Sure. Hi, this is David Ebersman. I work at Raytheon. Years in the industry, I don't know, 25 or something like that. And we're doing some HALT test planning on a few of our programs. So I'm just sort of curious what your experience was.
All right. Next, I have Glenn. You can go ahead and unmute, Glenn. There you go.
Sorry there. I got another phone call. My name is Glenn Krasinski. I'm with Weiss Technique North America, and I've been in testing for about 10 years now.
All right. Next, I have Jordan.
Hey, yeah, Jordan Wetzel. I'm a structural dynamicist at Lockheed Martin, and so we do a lot of electronic packages and screening and modeling and trying to predict fatigue. And so we've had a lot of interesting things come up recently with HALT and HASS. So
next, I have Mark.
Yeah, Mark Kamenzen. I hope you can hear me. So I'm a member of IST for about 30 years, more on the analytical chemistry side for clean rooms, but I also developed methods for looking at the purity of environmental test chambers, looking at all the issues of what's the purity of the water going in for humidity part, what's the CDA for dry down, how clean is it crappy dirty air or clean dry air, and then what stuff mucks up the walls and the outgases from the seals. And then if you overload a environmental test chamber, sometimes things outgas and cross-contaminate. So the loading actually does that. So we did some studies on that, published papers on that.
All right, thank you. Next I believe it's Vinay.
Hi, this is Vinay from Rentec Power Systems. Been with the company about 10 years. We do a lot of custom magnetic design, and so really interested in how do you put together an accelerated model for highly customized parts.
All right, thank you. Next I have Julie.
Hello, my name is Julie Jennings, Lockheed Martin Fellow in Huntsville, Alabama. I've been in industry about almost 27 years. I predominantly do environmental testing, and I'll be kind of leading your session today.
And then our first panelist, Giulio Polito, you can go ahead and introduce yourself.
Yeah, I am Dr. Giulio Pulido. I work for Phononic. This is as a Vice President of Global Quality and Reliability Engineering. And my area is specialty is structural fatigue analysis, design for reliability, testing, accelerated life testing, HASS, HALT. So we will be talking a lot about that today. Thank you for having me here.
Yeah, and then our next panelist, Dustin Aldridge. You can go ahead and introduce yourself.
This is Dustin Aldridge. I work at Raytheon Missile Systems and Defense in Tucson, and I've been involved in environmental testing for, I don't know, 35 or 40 years, primarily in vibration and thermal, but also with corrosion and other aspects. And here in Raytheon, we certainly do a fair amount of ESS as well as HALT testing in the development of products and things like that.
All right, so just to talk about today and how it's going to work. So it's very casual. So what we'll do is we'll first start out, if anyone here has any specific questions or scenarios for our panelists, you can go ahead and just unmute yourself and verbally ask them, and then we'll get to any common questions that we see in the industry on these topics. So first, I'm just going to open it up, and you can unmute yourself and ask a question. Any questions? Go ahead.
I'm just always interested to know if people have had many issues with the purity of environmental test chambers. I mean, we put witness wafers in NASA test chambers and find out what lands on the surface, and looked at like LEDs burn in when you're doing a whole bunch of them at once. They can cross-contaminate because you have so many in there, or if you're doing laptops or cell phones, there's a lot of overloading issues sometimes that the test can bias the test.
Dustin or Julio?
Well, the aspect of overloading the chamber is, yes, a very can be a common occurrence. It's mostly with our vendors, okay, when they try to do some qualification, or we'll say that we're going to do an ESS test, and it turns out that they've loaded the chamber so much that they really are not getting the temperatures on the product at times, or even the change rates and that sort of thing. And so we have to go in and actually do the monitoring of the chamber as well as the parts, and then say, okay, you can only put in 5 of these units. You can't put 40 in there, okay? Because so we end up qualifying their test profiles that they have. So I have seen that. I don't know about the contamination aspect. We don't have that kind of an issue as far as I'm aware of.
Well, I mean, you can haze optics, you could cause corrosion, you could cause a lot of just landing of organics that affect conductivity of things. So we've seen a lot of interesting issues.
Yeah.
Okay, all right.
Yeah, one thing that is important to consider is that when you are doing a test, you need to make sure that, yes, you want to get as many parts as you can internally. I understand that, but you need to also make sure that your test integrity, the integrity of the test, is perfect. Are your temperatures, are your humidity, is any contaminant going in? So if parts are going to generate potentially contaminants very close, you want to make sure maintain a integrity of the environment. You need to look for that. You need to be able to measure that, because it doesn't matter if you close the chamber, but if you are looking to a temperature, do I get a temperature uniformity profile temperature across the chamber? Are all the parts cooling and heating at the same time, for example? In the same way goes for the humidity and all those concerns. So it's extremely important that the person who is designing the test, the person who is setting up the test, understand what is needed to control the integrity for the given test, right? That is the important part. That defines. If you're going to test for temperature and you're going to generate heat, you may need to dissipate that heat, for example. If you are doing the humidity test, what is the temperature you should be testing, in what kind of levels? Is this high temperature, low temperature for that given humidity? Because you have different behaviors, and are those behaviors representative of your use case? So your use case is what usually drives, number one, the test, but also you need to maintain that integrity of those components. I hope I did answer correctly for you, to give you an idea.
Any other questions? Oh, go ahead, David.
Yes. So I guess I have a question, kind of more general question, right? Like, when is HALT testing the right tool in the quiver?
That's a really good it's a really good question. Sometimes Julio or Dustin, would either one of you like to take a stab at that?
Oh, I take a stab. It would be my pleasure. Um, Usually, the HALT, HALT, and ALT. Let's be clear on this. HALT, you cannot determine statistical values on that. Well, you cannot. Live, it will not be. ALT will define that for you. The HLT validity has its place. When you don't know your limits in vibration or temperature or humidity, you need to know what is the point where I change my state, which is what I call state change or failure happens, right? So you will take your parts. Imagine if I'm doing a constant test temperature, and because I want to drive this degradation due to Arrhenius, right? Then what I want to do, okay, what is my limits on the temperature? Do I generate the same failures that I'm expecting to happen? Are those failures related? I'm not generating higher failure mechanisms once I go. What are the limits of my part? So you want to determine what are those limits and destructive limits is a great test, especially in electronics, because electronics sometimes you start seeing intermittent behavior. So what you want to stop the test before intermittent behavior because you don't want that to happen in the field in most cases, right? You don't want intermittent behavior for different reasons, noise on the response or whatever. So certainly you want to determine those parameters and then you start testing on those parameters, assuming a failure mechanism. Now, HALT is powerful on that. You need to understand you should not use only HALT. HALT should not be used only. Should be as a basis for understanding the limits of your design and then moving into as life testing. That will be my simple summary. Okay. Now you can learn tons from HALT. If you are using that as a developmental tool, right, versus a demonstration tool of reliability, I'm just then you can start having a process where you okay, let me see how I can make my part more robust. Making your part more robust doesn't mean you're gonna get higher reliability. And this is one thing that people need to understand. Robustness does not equate all the time to reliability because reliability has to do with a given condition. And the chamber, you could be stressing to a level that is not representative of the use level. So therefore, you cannot generate reliability. So one thing that is important is a very powerful tool when you are designing and increasing the robustness of your design. But every time you increase the robustness of your design, you're increasing the cost of your design. So this is something that you need to account for. And once you identify the right level of robustness that you need, then the question is, what is my reliability? And that's when you turn to, okay, I got the limits, and now I can decide, do I do a cycling base, where you repeat a use level type of base, or you move into a different level, which will be a stress-based test. That's are my 2 cents. And by the way, that goes for thermoelectric, everything that goes associated with that.
Okay,
Does
thank
that
you.
answer your question, sir?
Yeah, thank you, Julio. Yeah, no, I think the one thing that I took from what you said is one reason is to determine the limits of the product. So for electronics, maybe you could shut it down before it reaches those limits, as an example. And then yeah, you're saying otherwise it's part of a mix of things you can do. All right, thank you.
Yeah, now one of the things I want to say is that you have to be able to do, HALT is a certain process, which means that you are monitoring while you're doing your testing. And it also has to do with the number of parts that you have. If you have a very low production, like we do in a lot of the military stuff, we cannot do really the HALT process as it would be, as is recommended in, simple electronics and, office equipment and this sort of thing. So you have to look at what you can reasonably do with your product. And if you don't have the ability to monitor, that reduces the amount of value you can get from your HALT process because you're not going to be able to detect when, intermittent failures occur and this kind of thing. So it does require some judgment as far as what you can do. If your hardware, costs you $2 million a piece, you're not going to have two pieces to destroy. So, but if you're making 1,000 a day, you can do it pretty easily. And if it isn't very hard to monitor something, then it's easy to do, but not for some of these major systems.
Yeah, I think the point that uh, Dustin is bringing is extremely important, right? Just because you are doing one HALT or HALT or ALT, whatever you are doing, please instrument your component. Understand the different factors that you want to evaluate. You need to look at what are the factors that are occurring, what are those factors drive my failure mechanisms. Those are the things that Dustin is trying to say, in my opinion, is very important. Because if you don't get information, you just testing for testing. There's no value in that. Very good point, Dustin.
Yeah, I wholeheartedly agree. All right. Anyone else have a specific question with regard to HALT? Or its sister HASS?
Do people have an idea of how to develop your HASS from your HALT?
Well, so hey, Dustin, maybe we talk about what the benefit of HASS is, and then how do we get from HALT to HASS?
Yeah. Okay. Well, the benefit of HASS, in my opinion, is that you've understood something in terms of the performance of the product to define those limits for your HASS. And in the general ESS stuff, what is often done is that we just say, oh, we're going to use NavMat, we're going to use just do 10 cycles of temperature cycle between minus 29 to 85 C, some generic requirement that we've used for years, whereas HASS is based upon knowledge of something. So, that's what I think is that is the benefit of the HALT HASS process, okay? But HASS actually has a basis for determining what those levels are, whereas ESS can be just arbitrary.
Okay. And and if we use HASS properly, in theory, we should be able to execute a HASS program in a much faster overall time frame, right, than a more traditional ESS program.
I have another question, if you guys don't mind. I've seen an instance where for a program just decided not to do EQT at like a lower level, and sort of defer it to a higher level, and instead do some HALT, like instead. Have you ever heard of that, or any thoughts on that?
So
You explain to me what is EQT?
yeah, that was my question. Are you saying environmental qualification testing?
Yes. Sorry.
Okay. No,
My
that's
God.
okay.
We are good at creating names.
Well, we're kind of way off. When you're talking HALT, you're way off in the, in the fine print, right? So I assume everybody would know it, but maybe I'm wrong. Yeah, I'm sorry.
No, you're fine.
No, that's okay because everybody generates a new jargon. At the end of the day, if you think about it, it's almost everything is the same. It's what is your objective, right? Do I want to do it fast? Do I without because of stress? I want to do it I want to do it benign. And I think Justin is extremely right. You can do it ESS or HASS. You are gonna eat life of the product. So the question is how you go about designing it correctly. What is your objective? Is your objective to get the infant mortality out of your line and to a given failure rate, and then from that use that now any product to go in the field? And if you do that, how much life you are eating out of the product by doing that acceleration or that test before it goes out, right? So we are very good at creating different types of jargon. But the important thing at the end of the day, if you look at the bathtub, is number one is a classical bathtub, which is not really in life, but usually you want to get out the infant mortalities. There is a target failure rate that you want to eliminate. And most of the time you do that because you don't control those factors. Your manufacturing process or your design cannot control those factors. So you just want to take them by test. And then after that, you use your failure rate and try to drive that. So how you do that, that requires for you in a study understanding what is that behavior, what those stress factors are, what is the probability of those, me taking it out. So it's in a study. It's not sitting just in a corner and say, oh, I'm gonna do 10,000 cycles or 5,000 cycles or 1,000, one cycle at this stress level, and it's gonna eliminate everything. You need to have some testing behind, some test design behind, because the HASS, the ESS, and anything else associated with the line where you want to control, screening, that's the word. You want to do a screening, a stress screening. You fast or slow, no matter what, it's a stress screening. That's what you want to do. Then you need to understand what is the stress, how that affect, is that in line with my failure mechanisms? And second, and last, I should say, is once I do that, how much life I consume of the product and what is my expected life from that point on. Thank you. I hope I answered your question in a better way.
Thank you. Yeah, no, I think you've kind of answered the question of actually why is it another reason why it's needed, you're saying, is to target a failure rate from the field. You're saying if you have a failure rate and you're not happy about it, that would be another reason to do HALT, right? Is that what I heard? Yeah.
One thing I would say, David, and maybe it depends on how you execute the HALT, but a lot of some of the stuff we've done recently has been on repetitive shock, and repetitive shock chambers. And so, for an EQT, you're typically given environments, in terms of, say, acceleration, power spectral densities or something like that, where you have a spectral component to it. But oftentimes with those repetitive shock chambers, you're not dialing into a specific kind of acceleration power at a specific frequency, and so for us, we have a lot of electronic components where the fatigue to those components is driven by the natural frequencies of your assembly. And so, to try and equate any sort of repetitive shock type of HALT thing to the damage that might accrue from an EQT, to Julio's point earlier, it's like, it's extremely hard to do. I don't know how you can make an argument to replace an EQT with HALT, kind of for that reason, for most things.
Yeah,
Well,
one thing is
David, I think what Jordan and Julio, sorry to step on you here, but to David's point though, it's when we started to replace a HALT for a lower level assembly, I think is kind of where the impetus of the question came from in the beginning, right? If we're going to go take the sum of the parts and put them into the next higher assembly, a black box, for example, and I don't know, that black box may have a couple of different black boxes included in it. David, I think your question was, does it seem logical sometimes to skip the environmental qual at the little sub-assemblies that go inside of that bigger whole, perform a HALT on that, get a robust product that's, that can stand those large, you've got the product built, so it's got fairly large robustness. Whether or not it can survive your actual environments is a different question, right? And then integrate those into the next higher assembly and do your full environmental qual on that assembly. That was the impetus of your question, right, David?
Yes, it was, yes, and I think actually Jordan answered part of it, right, which is that be careful because if you go to
Right.
repetitive shock chambers, you got to be that doesn't do it. You know?
Right, and so there's risk in doing that, right?
Yeah.
If you go perform the halt on the individual smaller lower level assemblies, and you significantly beat them up a little bit, and you find where they're in theory where their weaknesses are, but then if you haven't modeled properly or haven't done all that assessment properly, when you integrate them into the next higher assembly, there's a potential, there's that risk there that there's those gotchas that come out that you were unable to either model or predict or something like that, or accurately shake out in the lower level testing, the halt that you did. I think it's you have to weigh those things because your next higher assembly may not be something too elaborate, right? But if you go, let's say it's the size of a shoebox with a couple little boxes inside there, that might be okay until you bring it into the big assembly that may be the size of a small automobile, right? That maybe that's not the most appropriate way to do that. I would contend that that's probably like the worst example of what we can do, but it's not necessarily not been done before. So I think there is some level of goodness to be had there, and but to Jordan's point, I think you really need to just make a full it's hard to make those assessments at that point.
Yeah. I mean, for vibration, in the sense of vibration, my first question will be, it's a low displacement, high displacement, low frequency, high frequency. It's a road input versus sine type of input. So if I may not use a chamber, I may use a thermal chamber with the auto shaker because I want to replicate the low road input. So if that is what you want, a normal a whole chamber will not help you. Yeah, it will not help you in that sense because we'll not be able to generate the power spectral density representative of that application. Now, because at the end of the day, all you do, and if you do an energy pass, you are generating damage on all frequency levels in the road at all frequency levels. But usually the one you want to be away is from your natural frequency, right? You want to be away from because then you get that amplitude right there and the response, and then generate failures. And you want, when you're testing, if you're gonna test something at the natural frequency, you don't need to be that smart to figure it out. You're gonna fail because you are exciting at that level. Now the question is how frequent I get it, that frequency, how much energy is there, and then how it degrades over time. So in my 2 cents, I will suggest when you are performing that type of test, you would not, I would use a chamber. If you need to combine thermal and vibration, and there are reasons why you need to do that, in general, you would like to have a vibration
Shaker table.
a shaker table. Thank you. A shaker table that will allow you to get those vibrations levels there. Okay, that you need representative.
No, that's a good answer. Yeah, you're saying that. Yeah, use a standard shaker. Don't use the shock,
Yeah.
repetitive shock. Yeah.
Yeah. Now, if you are with electronics, those things are perfect for electronics, believe it or not. But if I am testing a system, if I have, I have a component, it has a natural frequency. This component has another natural frequency. Together, they have a different natural frequencies now together because I have the interaction. That is what you need to look at. So I may qualify a part for a certain level of vibration or energy degradation, but at the end of the day, I want to test, I think what Julie was indicating, you want to test at the system level to make sure that you integrated all the parts, because it's not only affecting by the actual component, but also the boundary conditions between those components associated in that system. I hope that answered your question.
The other thing is that in your you know, at your board level, that's doing that stuff. But when you go to the higher levels of assembly, it's all the interconnects that you're really worried about. And so, you know, but then there's a certain range of how far you can go with that. When things get too big, you just can't get enough energy into the thing with a repetitive shock system. The other thing I'll say is that you can look at the fatigue damage spectrum, which is another thing which has been, you know, they've looked at that you can make that or determine that from a repetitive shock or a electrodynamic shaker system. Uh, but again, you're looking at, you know, your response measurements and that kind of thing. So there has been some work on equating or looking at, you know, what the very relative damages from repetitive shock or from the electrodynamic shakers kind of thing. There's a number of papers that talked about that and how to do that.
Yeah, I was going to ask to that kind of to that point. I know so this is a question in terms of going from HALT to now developing a HASS kind of plan and profile based on your HALT results. I know there's pretty explicit direction in terms of okay for vibration specifically. You know, you reduce your kind of your vibration, you know, upper, I guess, the vibration operating limit by a certain factor to get kind of, hey, this is the magnitude of vibration we should use for HASS. I haven't seen a whole lot talking specifically about the duration of vibration that should be used for HASS. So there's a lot, I think, out there about the magnitude of kind of GRMS, I guess, magnitude for HASS, but not necessarily the duration that you should use. Should you use the full duration of kind of how long you vibed during HALT? That can sometimes be pretty, you know, a pretty long duration before you had any sort of failure. Or is there some sort of factor, you know, for
Oh,
that?
great question. Yeah, great question. Dustin or Julio, any thoughts on that?
Well, typically for HALT, you're doing 10 to 15 minute exposures at each level. And so, you know, the common thing is about 10 minutes, you know, um, for your HASS, because you're trying to do just look at, you know, getting the weakest parts out of the out of your production stream to protect your customer. You know, when you start taking yeah, and you want to also be certain that you're not taking out too much life out of the product. And so some of the things we do a fair amount of this is looking at the what is the fatigue life for some critical things, and then we make certain that we're below a certain percentage of that life that is taken out throughout the entire manufacturing process. So you may do things at a board level, you may do things at a system, you know, a subsystem level, then at a system level. And at each one of these, you may be doing some kind of a screen to look at interconnects or for component issues or you know, something wrong. And so you want to be certain that you're not inducing too much damage throughout your manufacturing process. And then you have to limit in the manufacturing process, say, well, you can't do this more than, you know, more rework than this many times because we have to keep this, the damage level down. There are occurrences where we have used up, like, say, 80% of the life just in the manufacturing process, and then you go out in the field and things fail. And that's just because somebody hasn't taken the time to really understand the limitations of the product they're working on. But it has happened that way. So, but I would, you know, say that, you know, it's typically designed to be relatively short because you're in production and you don't really want to take hours to do a stress screen. I mean, we get into this with SMC S016, which is a things for space systems, where they want to have 200 hours of burn in and all this kind of stuff, and they consider that to be a stress screen. But that takes so much time, okay, that you know, and we have things where you can't have them powered for 200 hours. They will burn up in 10 minutes, you know. So this is the kind of thing we have to, you know, talk about with customers about, and, you know, how to do certain things. But um, as a general rule, I think that we use on the order of 10 to 15 minutes is the typical duration for a stress screen, including vibration.
Gotcha. And do you typically kind of recommend or do like, hey, I've come up with this HASS profile that I'm going to use, and to your point, to kind of quantify, okay, how much percentage do I think I might be taking out of the unit with this profile? Basically, run that profile repeatedly a certain number of times or until failure. You know, like a proof of screen type of thing.
Yes, proof of screen is very important, and
Right.
it's not always executed, but it does protect you, okay? And if you can't do a proof of screen, you can use analytical modeling to potentially show it, um, as long as your models are well correlated. And so we actually do the modeling thing. We've also have done the proof of screen where you do 20 or even 50 times of the and to show that you're not taking up too much life.
Perfect. Thanks, Dustin.
Okay.
Hey, Dustin, you brought something up that I had a question about as far as, you know, the consumption of life during the production process. You know, some of those things like reflow cycles or, you know, even the lamination steps at the PCB vendor, you know, you can predict. But when it comes to rework cycles, there's a lot of variability on, you know, what happens during that rework process, depending on, you know, which components are getting reworked and the extent of what rework is being done. You know, what are there any predictors of, you know, how much life is being taken away or any guidance on limiting a number of rework cycles?
Yeah, I mean it's a valid point that we, you know, there may be, you know, certain critical components on your board, and the one that you're working on is like, you know, halfway across the board, and it really has very little impact on, you know, because you're just doing your hot air pencil or you're doing something else that's very localized. Um, but if you go through a whole, you know, generally there is, you know, all these components are set up to have, you know, three reflow processes. Um, and so you know that that is going to be, oh, that potential damage is always there, even though it may not be on every part. And so one of the things that we do is we say, okay, when you do your qualification, that you're going to go to the maximum levels of all those kinds of things that are allowed in your manufacturing process, which says if I go through three reflows, if I can have, you know, two reworks at this stage and three works over here at this stage, that you have done those things. Or and in those reworks, see, it's not the rework itself so much as the if the rework then generates, oh, we got to go through ESS again, okay? And how are you managing the rework process to from an ESS perspective or a HASS perspective is whether you do just complete, you know, from where you failed to the next step, or if you do the entire thing. Most of the times, manufacturing just wants to have a standard process, and they don't want to be keep track of, oh, it failed at cycles 3, so I got to now go between 4 and 10. You know, they just want to go, let's just do the whole thing. Okay, so what we do is they say, okay, you've got to go through all those different potential ESS processes, and then you can qualify that hardware, okay, after it's been through all that. And so that's how we address that.
In our side, just to give you an example, what we do, we usually we test, we do an ALT at a given stress We do another ELT at a given stress, establish the life stress relationship, determine what is your reliability function, probabilities of occurrence at given stress. And then we say, okay, if we test at that stress, we're gonna be taking X amount of life, and this test cannot be more than this time because our intent is to degrade at this stressor level, whatever is that, vibration, temperature, humidity, whatever you call it, okay, whatever is critical factor that defines your failure mechanism that you want. So we do, in general, two stresses, establish a relationship, establish what is the right life that we want to take, and then we take it out. And then we test for that. When it comes to failure, and imagine you are doing and you want to use those parts, then the criteria is where do you fail on that? If you fail before, whatever point you do, then what we do is, okay, if you repeat the test with those parts that fail, you fix them, right? You do fix them. You say, okay, I worked it out. The kicks, you put it back on test. We know it's going to take another life, another piece of life, because on some of the components except the reward. So we understand, okay, what is that failure degradation for those components? And then we just, okay, there's still a good life and good margin, we call it, for the life of that product based on that. But we base it on stress levels. Our times of testing are based on ALT tests defined, and then we generate the functions and define the time. And once we repeat, then we have, if we fail, then we know exactly what happened, and we fix it, and we just test a little bit more just to make sure that it works correctly, and that is all calculated based on that. I hope that gives you an idea how we do it.
Great comments. Anyone else? Let's see. Jordan, did that answer you? Did it help you?
Yep.
Perfect. Looks like we got about 12 more minutes left, so I want to be mindful of your time. Any other thoughts, questions, comments that are from the group? I know that the panelists probably have some other things that they would love to share with you.
I just have a sort of more general comment that comes out of what I was just listening to you guys discuss, which is it's interesting how, you know, you have this accelerated life over here, and then, you know, and then you have qualification and mill standard 810 and things like that, right? And thermal cycles don't appear to be, to me, to be a big part of 810, so you can qualify, you know, products without actually thermal cycling them. Not very many times. And you know, to your point, Julia, like when you do ESS or HASS or whatever, those are cycling events, right? So for some reason you need to do them for that, but you don't need to do them to qualify. I don't
Well, it's not
understand.
really true.
Yeah.
As a matter of fact, just to give you an idea, and you are right in the direction. When we are qualifying a product, we do the ALT. We understand what the failure mechanism. We are designing for the failure mechanism, right? Design engineering does their magic, and then comes back and say, and we work together with them in the process and make sure that, hey, what is the test that we need to do to demonstrate the life of the product with a certain use? That's what I want to demonstrate. At the end of the day, I just want to make sure I produce for my customers and they can use it without any problem. So I want to debug it. So I use the test data that I developed during the development side. My HALT, my ALT will be input to my manufacturing, and that's what a reliability engineer needs to do and determine, okay, we think that we have an unknown, right, factors of variance in manufacturing that we don't control. We want to clean that. So we want to test to a certain failure. So level on that condition. So this is the stress you need to use for this amount of time based on those previous calculations. And now you are having a quantitative way to control and determine what do you have and how it's affecting your product life overall. So it's about the life cycle product development, where you have the product development, you understand what you're doing, you do the HALT and the ALT, and then after that you come and say, okay, now I need to develop, I think we're gonna need a HASS. We think we want to make sure that we don't have issues here. If that is so critical, then because you're manufacturing, whatever reasons are, right? Then, okay, what is that we're gonna do? What is the exact test? And then you use the information for another previous test and validation. You should not be creating at that moment any test, any validation. It should be easy information that your reliability engineer transfer to your quality engineer, and your quality engineer pick up that, and then now they execute it as a control. You may use the HASS or ESS or EO, whatever a jargon we want to use, tests that we will control your production a certain level or minimum certain level quality that you want to deliver for your customers. That's all.
Yeah, I want to just say something about Mill Standard 810. Is that 810 talks about tailoring to your service life conditions, and so it depends upon what product you have. Now, I've been in automotive and I've been in defense, and so in automotive we have 50,000 starts in 10 years kind of thing. So that's 50,000 potential thermal cycles. Okay. And so, when you look at, in that case, what is the trip length, what is the temperature at which you're starting at, all these kinds of things to then define what is the number of cycles that you might have to do on an accelerated life test basis to simulate that environment. When you're talking about defense, we have a lot of stuff that's just sitting in storage for years. Or it may be in the case of like missiles, they're in a temperature controlled silo kind of thing. Okay, so when you start looking at, well, okay, over 20 years, what does and when you have a temperature change of 3 or 4 degrees C per day, maybe, what do you have to do in terms of your thermal cycling to look at low cycle fatigue, using Kaufman-Manson or whatever model you want to use, what is the cycles that would represent that life? And depending upon the materials, if it's a polymer thing, or if it's solder or some other material, you've got to take that into account. So, but the 810 is typically, you want to be tailoring to your real service life environment. And if you don't have those kinds of things, they may have some generic things that they used to do in 810D and stuff, but for the G and H, I think they've removed a lot of that stuff.
Dustin, you mentioned using Kaufman-Manson or its modified derivatives for taking those tens of thousand service life cycles into an acceleration life cycle. Is there any guidance, for unique geometry of solder joints? Because a lot of those curve fit data, was done towards standard SMT type product.
Yes. Well, some of that, is going to be dependent upon your finite element analysis of those types of solder joints that may be different. And then also, when you start looking at the coefficient thermal expansion going on, as well as the vibration aspects, you can combine those things, okay, in terms of the amount of potential stress that's developed and that can be combined as in addition. But for the most part, you're looking at just the research which has been done, which says, okay, your typical for solder joints is anywhere between 1.9 and 2.5 on that exponent for the Kaufman-Manson thing. And then if you start looking at Norris Landsberg, and they start putting in things with rate and dwell time and that kind of thing. You have to then define what those exponents are for those things. Okay. And the model may not be appropriate for your system. You start there, okay, but you don't necessarily end up there, because as you develop more experience with the failures that could occur due to thermal cycling and vibration, that you may have to modify those terms and just be beside what the general literature talks about.
But you can go through the literature, you can get it, and that's a good process. No question about it. It's a starting good process. But at the end of the day, there's no better than a representation of your data set via testing. Now, give and take, there are industries where you don't have that liberty of having so many components, but usually you don't test systems at that level. When you are testing at components level, you determine the reliability with those, and then you start modeling based on that. So there is a sweet spot where you need to, okay, what is the makes sense for me to test a component, and when do I start using now a modeling tool to determine the final reliability of my system. So depends on that, right? So I need to make a decision. It's a component-based test, or it's a subsystem, all-system test. I may use different techniques for that. Number one. Number two is I can start with any type of model that you want to start with to give you an idea what you need to be looking for. But at the end of the day, it's your testing that is going to define the parameters, or in case of electronics, your activation energy and things like that. And now you can start, okay, this is the right function that I should be using for my problem, for my design, for my operation and type of operation and environment, right? I hope that answers your question.
I think some of the difficulty, specifically with us, is we're such a high mix, low volume company. It starts to become unfeasible to try and take on that research for the customizations to, modify those exponents.
Well, then your results, have to drive it, and you look at your returns, okay, and say, well, is the model correct, okay, or is it conservative, or is it we're not catching stuff as we should?
Yeah, and not only that, imagine I have different platforms, a platform, and then from that I have different products, right? And I have low volume in each one of those products, but I need to test all those products. Well, you don't need to. You need to do an assessment, and that's where you use other tools. One is changing in this platform between product A and product B. It is a condition where product B will be more susceptible to an environment. So I use product B to test that environment because I know it's weaker. And whatever I get from there, I can translate for that. I can establish at least one time, I can do a test in one, demonstrate one level. And then the other one, I just do a special, just few samples just to determine, hey, what is my change in function, how it changed, right? Call it duty cycle. Is my duty cycle worse or better? Is my stresses, because the different material, higher or lower? Those are the things that that's about strategy. That is your strategic approach to product development, product reliability demonstration. What is my platform? Do I have several platforms? Can I test that so I can reduce the amount of tests? Once I test a component, now I encapsulate that component. Do I need to go to the same testing I did before for that little component now that is encapsulated? No, I just need to demonstrate the encapsulation. I just need to demonstrate that hey, it's tied to the environment, wherever that environment is. That's what you want to look. So you need to start a strategic approach for product development and product, what I call reliability development, right? It's a new performance, it's a performance of the product. So you need to go about, okay, this is my product, this is my component, this is my system. what I test at each stage on the process, development process, and how I make that a knowledge development. Because at the end of the day, what you are doing is building knowledge. And if you cannot do that to your process, you're gonna be stuck testing every single thing, every single time, and you are not gonna get out of that rabbit hole because you just keep testing and testing and consuming your resources. But if you approach it strategically, in terms of what you want to do, in how the final product will work, in how the different platforms work in different environments, then you can make a fair assessment of that. I hope that works.
All right, I think we do have to end for today, but I did want to let everyone know that Julio is going to be teaching an introduction to HALT HASS. If you do need an introduction course at our EduCon conference, registration is not open up, but it will be open up in the coming weeks, and it's going to be in November. It's either online or it's going to be in person in the Chicago suburbs. So I want to thank our panelists. Thanks, Julie, for moderating. Thank you, everyone, for attending today. And everyone have a good rest of their day. Thank you so much.
Thanks, everybody.
Bye-bye.
Great
Thank you
day.
so much.
Thank you, everybody.
Bye.
Really appreciate it.
Yeah.
Thank you.